Okay, can you hear me? Okay, so let me share my screen. So you can see the screen, right? Okay, so this in this exercise section, we'll continue to discuss things about the QED, but this section will be more mathematics. So let's start with the first question. So in the first question, we are asked to derive the analog for the antiparticle spinors of these relations. And so let's have a review of what this relation means and how we get it. So in lectures, we have considered a process of electron-muon scattering, and the Feynman diagram is like this. And we have derived the amplitude using Feynman rules. And so we can calculate the amplitude square, just taking the complex conjugate and multiply them together. So this is the amplitude square. And the next thing is to sum over all the initial and final spin configurations and average over the initial spin configurations. So if you don't understand what this means, I can explain once again here. So in this example, we have electron-muon scattering. So in the initial stage, we can have 4 spin configurations. And similarly, in the final stage, we can also have 4 spin configurations. And so in total, we can have 16 combinations. And the thing is that we usually don't care or don't know the spins of the 2 colliding electrons and muons. So we actually don't know which initial stage we are in. So that means each initial spin configuration will have a 1/4 probability. And now let's consider the first case. So we have 4 possible choices for these 2 spin up leptons to scattering. So we have 4 possibilities, and each will carry the corresponding amplitude square. And so the total probability will be something like 1/4 times the summation of these 4 amplitude square. Right, and similarly for the second one, we have 1/4 times, and we have 4 possible paths. So and so on. And so you can see that the total probability amplitude will be to sum over all these 16 amplitude square and divided by the number of initial spin configurations. So that's why we have this rule. back to this amplitude square, we have to sum over all the spin configurations of these 4 particles and divided by 4. And you can see that these 2 terms, it only relates with particle 1 and 3, so we can pull it out, and we can form 2 big summations. And you can see that these 2 summations, they actually have the same form like this. So now we can focus on simplifying this. And I think you have gone through once in your lectures, and I just repeat once again. So the first step, you can see that this is a number. So this U bar, you can regard it as a 1 times 4 factor. So it's something like this. And this gamma 2 is a 4 times 4 matrix. And this U is a 4 times 1 column factor. So the total result will be a number. And so the complex conjugate is equivalent to Hermitian conjugate because it's just a number. And the second step is to simplify this dagger, and you can prove it yourself easily. You just have to use U bar equals to U dagger gamma 0, and gamma 0 dagger is gamma 0, and also square equals gamma 0. So you can prove this yourself by using these 3 definitions and or properties. So substitute back this into the original expressions, can obtain this. You can simplify the expression to this. And the third step is to do the summation on the spin of B. So we can move the summation side to the middle and consider the summation here. And then we can use the completeness relations of the Dirac spinors. So I think Professor have proved this in class. And this slash notation, it means gamma mu p mu. So this is a 4 times 4 matrix. And just a note, more rigorously, there should be a identity matrix here. But as usual, we will omit this. So after using the completeness relations, we can substitute in here, and we just denote this whole 4 times 4 matrix by Q. Okay, I'm just repeating what have been said in lectures, and the next step is to use the index notations of matrix multiplications. So we just explicitly write down the index of these matrices. And since we have used the index notations, so now each term will just like a number, so we can move it around. So we can just move this Qij outside and consider these summations. And once again, we can use the completeness relations of Dirac spinors, but this time we consider spin of A. So substitute into this, we can get this. And the final step is to notice that the Qij and Ji will just be the trace of this 4-tensor matrix. So the trace is just the sum of all the diagonal elements. So that's how we get these relations. So here I put all the steps together, and you can see that only in these 2 steps we have used the properties of the U spinor, and so it now become very trivial how we treat the antiparticle spinors. So we just for any particle spinor, the completeness relation is like so we just replace all the plus sign by the minus sign. And similarly for the next case, we just replace the plus sign by the minus sign for one of them. Page 2, okay. Let me see. Okay. So this is just to play around with the probability, right? So we have 1/4 probability for each initial state, and each initial state we have 4 paths. So we just multiply them together and then add them up. Okay, so that's question 1. And in question 2, we are asked to substitute psi to be the 4 Dirac spinors and obtain the result. So let's try U1 first. So we just use the expressions for the U1 spinors, and the normalization is like this. And we can obtain each components by observation. Psi 1 is n, and psi 2, the second component, is 0, and psi 3, and psi 4 is like this. And for the complex conjugate, we just change plus I to minus I. And so let's consider the first component. So we just simply substitute all these components here. So for the first component is n squared, and for the second one is 0, and so on. And for psi 4, these two conjugate, when they multiply together, they will give px squared plus py squared. Right? And then you can see that this is just the total momentum square. And here I substitute the normalization factor. And then we can use the energy momentum relations. And then you can factorize this. And then you can cancel one factor here. And so the final answer will be 2e over c for the first component. And it's basically the same for other components. So for example, for the second components, we just substitute again, and these two terms will be 0 because it contains psi 2, and so we only have to consider these two terms and just substitute them. And after simplifying, you'll see that this equals to 2px. So it's just the same for the remaining components. So in summary, for U1 spinors, the 4 components will be E over C and Px, Py, Pc. And so you can see that it really transforms like a 4 factors. And you can try it yourself that all the 4 spinors will actually give the same result here. And it means that the spinors actually contain more information other than energy or momentum, right? Because all these 4 spinors give the same results, but they are considered different. So they must contain more information other than the energy and momentum. For example, the spin in some sense. So I think that's all. Do you have any questions about exercise? Next case. So just do it more clearly so you can see that here particle A and B are all antiparticle spinors. So all of them replaced by the minus sign. And here particle B is antiparticle spinor. So we just have to replace this by the minus sign. And similarly here, we just have to replace the minus sign for the A particles. Okay. Okay. If you have no question, then we can stop here. Okay. Goodbye. See you next week.